thank you, and thanks to the organizers for inviting me to give this review today. So yeah, I'm going to use the occasion that there is a talk right after about dust properties in nearby galaxies to focus on gas properties and spectroscopy. So to get things started, physical processes such as star formation act on, or at least they originate from various spatial scales. And this is illustrated in this nice figure here, where you have the transition from the atomic gas to the diffuse molecular gas, and then the fragmentation and collapse that leads to star formation, to the dense molecular gas, and then eventually to star formation. And you go from kiloparsec scale to less than parsec scales. The challenge for extragalactic observations is that you need to reach these small enough spatial scales and wide range of scales to disentangle the ISM components, or as we will see, at least to recover them through indirect integrated signatures. And the other challenge is that we need to understand and generalize physical mechanisms that are happening in conditions that are very different from the Milky Way. So we live really exciting times because we have access to beautiful observations, exquisite observations, which I illustrate here with observations of two nearby galaxies with the combination of MUSE and ALMA data here on the left and HST and JWST on the right. And what that means is that observers need to digest and process a wealth of spatial information, while modelers need to combine different models with state-of-the-art radiative transfer and chemistry codes with complex enough geometries. What's interesting about nearby galaxies is that you have access to a wide range of in the parameter space, and the environment is different at large. For instance, the metallicity, but also the mix of different ISM phases. And you can also study the different predominance of physical processes. And I will mention the photoelectric effect on those grains, but also X-ray photoionization. The main obstacles is that a lot of these processes depend on the dust properties, and you have to have accurate knowledge of the dust properties in different environments, and also of the energetic sources. And of course, you have mixing biases when you have no spatial resolution or little spatial resolution. And what's the knowledge you gain in nearby galaxies, you can then adapt it to the early universe. And now it's been quite a few years that ALMA or NOEMA give us access to several lines in very high redshift galaxies, 6, 7, and they already show the multi-phase ISM nature of these galaxies with the lines like C2 and O3. But also what's more is that the spatial information becomes also increasingly available, which is illustrated here in a redshift 4 lensed galaxy with ALMA, where you have spatial information for CO, H2, and C1. And this is also illustrated here, where some IRAG blobs become what seems to be red spiral galaxies around cosmic noon between redshift 1 and 3. So even though you gained some information on the spatial structure of such galaxies, one thing to keep in mind, though, is that JWST, for the most part, will not be able to resolve spatially and spectrally more galaxies with a redshift more than 3 or so, especially for the spectra. The interesting thing about nearby galaxies is probably the fact that you can access low metallicity sources. So here is the metallicity versus the stellar mass for thousands of SDSS galaxies beyond redshift 0.2, with redshift less than 0.2. And you have several other sources in the local group, the Milky Way in green here, and you have local group galaxies in red, and red in blue. This is the LMC and SMC here. And what I just want to show is that by accessing the LMC and SMC, you reach quite low metallicities already as compared to the Milky Way. And you can reach even lower metallicities with other dwarf irregular galaxies or dwarf spheroidal galaxies, down to very low levels of enrichment. And what's interesting is that such metallicities, they will correspond to the metallicity. They will allow you to probe an ISM that is as metal poor as some higher mass galaxies with a higher redshift. So the absolute calibration here, this is from simulations, the absolute calibration is not very accurate, but the trend is pretty robust. And so this means that effectively, even in the nearby universe, we can study what a metal poor ISM looks like and try to understand the metal poor ISM that will be and the physical mechanisms that will happen at high redshift. These are some illustrations of the diversity in the ISM composition and physical conditions in nearby galaxies. This is showing the dust to gas mass ratio as a function of metallicity and the abundance of small amorphous carbon. This is showing the CO spectral line energy distribution in various sources, especially the high CO transitions, which reveal various heating mechanisms. And for probably a lot of them, these are a mix of different heating mechanisms, such as cosmic rays, shocks, or X-ray ionization. This is just showing the variety of molecular anion ratios in one particular galaxy, M51. And finally, this is the C over O ratio versus metallicity in the gas phase. And it shows a dependency with the metallicity. And it is something that we need to account for when comparing observations to models. The diversity is also seen in the radiation sources. So talking about young massive clusters, this is the size of some of the massive clusters that are well known versus their mass. And in the Milky Way, you have Western Lund 1 here at a few 10⁴ in solar masses. If you go just a little bit beyond, you have R136 in the LMC. And then if you go beyond the local group, you have much more massive and much more luminous young massive clusters, which means they are very interesting targets to study, for instance, the feedback on molecular clouds and on star formation. In such massive clusters, you might find high mass X-ray binaries. They have received little attention, although they are very important because they often dominate the high energy output from nearby actively star-forming galaxies. And they will typically provide about 1 to 10% of the total luminosity. It's especially important in the metal poor, dust poor ISM because the feedback may keep the ISM warm without removing a significant gas fraction. And what's interesting also is that there is a higher abundance of such sources, and they are more luminous at low metallicity and also at high redshift, the redshift dependency being probably a metallicity dependency. And so all in all, because there are high mass X-ray binaries, the mass of the stellar accreting partner and also the known correlation between the star formation rate and the X-ray luminosity implies that such sources, the X-ray binaries, are probably produced in young massive clusters, or they can be present already in massive clusters, or they can be produced and then be kicked out. And sorry, this is just the number of ultraluminous X-ray source per SFR unit versus the metallicity. So at low metallicity, it increases. Now, if we talk about the cold ISM within the galaxy evolution context, this slide is just to show the importance of gas in setting the star formation main sequence, which is here, star formation rate versus stellar mass for different redshift bins, redshift, low redshift here, high redshift there. And at low redshift, what you see is a band here, which is well reproduced or well understood by the profile of the molecular mass versus the stellar mass here. So the star formation sequence follows the mass of molecular hydrogen, while the scatter, which is not shown here because these are stacked data, but the scatter follows the molecular gas fraction. At high redshift, it's hard to see the band, and these high redshift studies will rely on the dust observations and the dust to gas mass ratio to get to the gas, to the molecular gas, because CO observations are very expensive in high redshift studies. But globally, the time-independent shape of the main sequence suggests long star formation duty cycles as opposed to quick up and downs around the main sequence due to the star formation history. And all in all, the equilibrium of gas accretion, star formation, and gas outflows are encompassed in the so-called gas regulator model, that really show how gas is central to the understanding of the star formation main sequence. If we talk about the cold ISM within the star formation context, so I already showed that the star formation is set on processes acting on different spatial scales. We know for a long time that CO doesn't trace the dense molecular gas, so we need to reach denser gas tracers. When we do, for instance, with things like HCN, this is IR to HCN, and this is H alpha over HCN. So it's a measure of the star formation efficiency, IR being the star formation rate, or H alpha, and HCN, the reservoir of dense molecular gas. And the consensus is that this decreases, the star formation efficiency in the dense phase decreases as a function of the interstellar pressure, or the dense gas fraction, or also the stellar mass, stellar surface density. And so the fact that this star formation efficiency is not constant leads to some questions, because you would expect a universal depletion timescale above a certain critical density for some star formation models, like the dense gas threshold star formation models. So the question is, do these models remain valid? And is it a problem of spatial scales? Is it a problem of higher critical densities? We need to get denser tracers. This is rather small spatial scale, so it might be that we need lines with higher critical densities. The alternative being that we can also turn to turbulence-regulated star formation models with feedback that would naturally explain such behavior. Now, what physical processes can we explore in a comprehensive way in extragalactic observations? So I already mentioned molecular clouds. I will also talk about them a bit later for the conversion of the dense to a molecular gas. The star formation process itself, I'm not going to talk much about it on parsec scale, so I'm just going to mention it very briefly. But you can turn to the extragalactic, to the external galaxies to study protostars, star-forming filaments, or cloud-cloud collisions. The best targets for that will be the Magellanic Clouds, especially with the SMC with 1/5 solar metallicity. Here, this is an observation of hot cores in the LMC, about half solar metallicity, with complex organic molecules detected with ALMA, and with chemical differences that between hot cores that suggest chemical inhomogeneities with due to mixing of gas with different metallicity, but that's quite debated actually. And of course, there will be much more to come with JWST and ELT, so a lot more observations such as these. Now going a little bit to different other physical processes, turbulence. So we had Benjamin tell us about CH+, which can trace out of equilibrium H2, and in some specific cases also possibly the dissipation of mechanical energy in turbulence, with some examples at high redshift with shockwaves powered by hot galactic winds or turbulent gas reservoirs, and there is a talk by Alba at the end of this session. A brief word on magnetic field. SOFIA is ending its operations right now, but it's leaving behind a legacy program of 14 nearby galaxies with really beautiful observations of the magnetic field, and a lot of papers coming out this year. Unfortunately, I don't have time to talk about them, so I will pass and give some highlights now. First, about the CO dark molecular gas. So I will refer you to Sumadan's talk after in this session. But just briefly, it's been known that if you do baryon counting through gamma rays, you have more baryons than what you can count with CO or H1. And so it's about diffraction, but it depends on the environment, especially on the extinction. And it seems to be most likely CO dark molecular gas, CO dark molecular gas, as opposed to optically thick H1, because diffraction doesn't depend on the optical depth of H1 or the excitation temperature of H1. In SMC or LMC star forming regions, the fraction of the dark molecular gas is huge. It can be 80 to 90%, which leads to an alpha CO, which is the CO to H2 conversion factor, much larger than in the Milky Way. But if you account for the filling factor of the CO clouds, if you measure it, if you account for it, then you find an alpha CO that is not so different from the Milky Way. And that confirms the fact that it is probably a metallicity effect. And that's supposed to be illustrated here. I mean, that's what we understand happens. At solar metallicity, you have H2 and CO here with a layer of C+, atomic hydrogen. At low metallicity, because of the dust abundance that is lower, the UV photons are able to penetrate deeper, photodissociate CO while H2 remains self-filled, leaving a layer of H2 molecular hydrogen with no CO here and small CO clumps. So that seems to be confirming, this seems to be confirming the results that we find. C2 and the other emission lines, like C1, for instance, they are very interesting for extragalactic observations because they are available potentially at very high redshifts. And from the models, for instance, those of Thomas Biswas, C2 and also C1 become increasingly good tracers of the H2 column density profile in the cloud, at low metallicity and for cosmic ray ionization rates that are as high as this. So this is for a single cloud. Now, if we turn to the dwarf galaxy survey, which Sumadan will mention, these are metal poor star-forming galaxies. Here we will study the integrated C2 emission of galaxies. And in such a case, we find a fraction of dark molecular gas reaching up to almost 100%, with the molecular gas mass traced very well by the C2 luminosity. This is, and that's the alpha CO conversion factor as a function of metallicity. So it seems to be quite well behaved as a function of metallicity. But the important thing is that it is for a single 1D model, where the extinction here is going to be traced by C2 over CO, and this is the main parameter. If you turn to more complex geometries, you don't find quite the same thing. You still find that MH2 follows well C2 luminosity, but the alpha CO is not a simple function of metallicity anymore. And what I mean by different geometry, it's illustrated by this figure here. You have a central cluster, and instead of having one model, we're going to mix a bunch of models with power law distribution, for instance, for the ionization parameter, for the density, and also for the depth of each cloud. And when we do that, we find that the alpha CO is actually a strong function of the depth of each cloud. And we seem to have, so this is the alpha CO versus metallicity, we seem to have two regimes, one where the alpha CO is pretty close to the Milky Way value, and this corresponds to galaxies for which CO is powered by very few dense and deep components, even at quite low metallicities. And then we have other population of galaxies that's for which CO seems to be powered by shallow components and dominated completely by CO dark gas. Now, continuing into the PDR and about pHs, there is overwhelming evidence now that the pHs trace very well the gas heating in the neutral atomic gas, and more than that, that the pHs probably are the main carriers for the gas heating. This is shown here. This is theoretical calculations. These are the black curves showing the photoelectric heating efficiency as a function of the charging parameter, and this is by Olivier Bernet. And the observations are shown in here in good agreements with the theory. The observations here are actually showing C2 plus 1 over pH, which is an observational proxy for the photoelectric heating efficiency. This is just an accumulated piece of evidence that the pHs are important for the gas heating. In the Magellanic class star-forming regions, what we've seen is that the C2 plus 1 over pH is actually pretty narrow, pretty tight, much tighter than if you use C2 plus 1 over TIR, for instance. And then you have this group of values here which stand out. These come from the smaller Magellanic cloud, not the LMC. So these are LMC regions, and this is the SMC. And so what's happening with the SMC? Well, we think it's a metallicity effect. 1/5 solar metallicity, because at some point the photoelectric effect on those grains or pHs is bound to fail, because the dust to gas mass ratio is going to reach a small enough value that you don't have enough dust, and at the same time we know that the pH abundance also drops at low metallicity. And that's what we started seeing in this figure. This is the photoelectric efficiency, heating efficiency versus the metallicity. And at some point, you reach values that are impossible. This is above the theoretical, maximum theoretical heating efficiency. And so what's happening here is that either the pHs, either there is another dust population that compensate for the lack of pHs, and it's still the photoelectric effect happening, but with a different dust population, or it's a different gas heating mechanism altogether. And this is, so you need to go to very extreme sources with very little dust to show that. And this is the case, for instance, in 1VK18, blue compact graph galaxy 18 megaparsecs away, with a dust to gas mass ratio extremely low. And thanks to some models, so I'm going to pass here how these models work, but what we see is that in the radiation bounded sectors of this model, the main heating mechanism is due to photoionization by a single X-ray source, which is right in the middle of the cluster here. And the photoelectric effect heating is actually very small, almost negligible. So it means it shows the importance of X-ray sources, but it also has important consequences for lines such as C2, which in this particular case doesn't trace the CO dark molecular gas, but a purely neutral atomic gas. Very quickly, X-rays and the cosmic rays are very difficult to disentangle in models because they have a similar heating mechanism. In extragalactic sources, we tend to use the fiducial value in the Milky Way disk, but we know that the extragalactic observations all suggest Milky Way-like range values between 10 to the minus 16 and a few orders of magnitude more in the nucleus, like in the galactic center. Yeah, I'll go quickly. With GWST, we expect minimal results for the diffuse large-scale ISM with near-infrared H2 line emission or H3+. So I think it's going to be interesting for prescriptions for the extragalactic ISM. I think I'm running out of time. I just wanted to mention the FANGS results for the timescale for molecular cloud formation. I'll skip on the method and go directly to the result, which suggests inefficient star formation due to short-lived molecular clouds and rapid feedback. Thanks to methods that maybe you have seen before, you can measure the timescale for the CO-dominated phase, the feedback phase, and the H2 region phase. Typical results is that in the LMC, the GMC lifetime, giant molecular cloud lifetime, is about 11 million years. In main sequence galaxies, a bunch of main sequence galaxies, it's about 16, with a wide range of values. These are the orange bars here. And this range of values, it seems to correlate with the stellar mass, and it's thought to be attributed to the CO dark molecular gas at low metallicity. But the key point is that the stellar feedback happens in very short time scales, 1 to 5 million years. This is the light purple here. And so early feedback mechanisms efficiently disperse the molecular clouds even prior to the supernova explosions. Last word on observations. So I talked about resolved observations. Now if we turn to unresolved observations, this is the visible range, JWST, NIRSPEC, MIRI, ALMA, NOEMA, and SKA. Now there is a sweet spot at redshift less than 2, where you have the UV lines shifting to the optical, as usual, you know that, the optical shifting to NIRSPEC, which is interesting, the near-infrared shifting to MIRI, and the CO ladder with ALMA or NOEMA, and SKA with the H1 here. But there is another sweet spot for unresolved galaxies, which is at redshift 7, where you have a bunch of tracers and UV diagnostics falling into the near spec range, including these lines that you might not be used to, but in the rest frame, they would fall at between 1400 and 1900 angstroms, and they provide accurate diagnostics for a bunch of physical parameters that are very interesting to measure. The far infrared lines will fall into ALMA, so some lines are already observed, and some CO lines falling into SK. So it's really a sweet spot. But one thing I want to draw your attention on also is that between JWST and ALMA, there is the whole far infrared rest frame that is missing. And it means also that all the mid-infrared features that should shift in the mid-infrared, far infrared, will be missing for redshift about between 2 and 10 in the near future. So a future far infrared spectroscopic explorer will be very useful, such as PRIMA, and I encourage you to look at this website to know more about PRIMA and the French involvement in that mission. Okay, so I think I don't have much time now. I just wanted to mention a few words about models themselves and what we need to account for in models when we do extragalactic observations. We need accurate prescriptions for the ISM and the energetic sources. We need to care for all the physical processes, the shocks also, which I haven't mentioned. And we need to account for the ISM complexity, which means the distribution of matter and phases, account for the geometry of the gas and sources, and something that I won't have time to mention much, but the high level of degeneracy, because we have large grids, a lot of degeneracies due to the fact that we mix a lot of things in a beam. And so you have various ways of doing it. You can do simulations which have various advantages. You can even do 3D radiative transfer post-processing on them, for instance, with Moccasin. Now, it's difficult to compare to specific observations, but as Benjamin said, you can do, you have statistical significance with them. You can turn to 1D models to do single cloud approaches to model a full galaxy. Now, a lot of people do that. The advantage is that you use state-of-the-art radiative transfer and chemistry, but it's difficult to scale to complex geometries, obviously. Then you can do pure 3D. This is the grade, of course, it's very nice, but you need to have a priori information on the geometry, so where the gas is located, how it's distributed, and same thing for the energetic sources. So the geometry is not a free parameter. You can do Monte Carlo 3D, it's a good 3D approximation. Again, geometry is not the free parameter. You can do pseudo 3D from 1D, so it's a combination of 1D models with angular laws to combine them. The advantage is that you use 1D models, so it's state-of-the-art radiative transfer and chemistry. It's well adapted if you have a central ionizing source like AGN, planetary nebulae, H2 region. The problem is that it's not pure 3D and geometry is not a free parameter. And finally, you have what we call topological 3D, which is a combination of 1D models. The advantage is that you can infer the geometry, it's parameterized, and but the disadvantage, of course, since it's not pure 3D. And just to finish, I'll show two examples of what we mean by topological models. This is one example where we have several what we call sectors. So this is a sketch of a galaxy with different regions. We assume that the clusters are surrounded with different gas clouds that we distinguish into different sectors. You can even combine the clusters, assuming they share the same properties, and have these kind of models with matter bounded and radiation bounded sectors. It's not 3D. You have problems with the diffuse emission, reflected emission, but the point is that it's much better than a single 1D model. Now you can do more complex things. This is a galaxy model with several H2 regions. You can assume they have the same densities, the same ionization parameter, or you can assume they follow some kind of statistical distribution for the ionization parameter. That's one thing. You can also have a statistical distribution for the density, which then you have a more complex law, and you can also have the depth of the clouds, which is related to what I showed before for the CO dark molecular gas. And this is very powerful. This is what we started to use notably in Lisa Montbazon's paper on the escape fraction of star-forming galaxies. There are some other approaches, like global SED approaches, that like SIGAL or BEAGLE, which you all know. In this case, it's more adapted to galaxy evolution parameters with more emphasis on the stellar population, stellar prescription, and maybe with two simple ISM descriptions. Although the developers actively work on the PDRs and CO, for instance, for SIGAL. And so I think while the first models I showed were focusing more on the ISM itself, the structure and the topology, and putting the focus on that, here the focus is on the stellar population, the stellar prescription and the galaxy evolution. I think eventually all these models should improve together to improve everything at once and have a reliable prescription for anything that is in the galaxy, basically. And just to finish, this is my last slide. The way to combine models to interpret a single spectrum is still going to be a matter of importance, even in the JWST era. Like I said in the beginning, JWST will have a bunch of spectra like this one at high redshift that will be especially unresolved. And the point is, how do you extract the most information from such spectra to go beyond simple metallicity measurements, etc. And so it is an important prospect to be able to combine complex models in order to interpret this and export the methods that we have built for nearby galaxies to the high redshift universe. Thank you.